Hello, welcome back to Learn Physics. In today's topic, we are continuing with the system of particles and rotational motion. So, in last video, we learned about the moment of inertia and the torque and power, all those things we learned. Isn't work done and power, how to find out all those things, isn't it? So today we are going to study about the angular momentum about a fixed axis in rotational motion. Okay, angular momentum. Angular momentum, already we learned it as angular momentum L equals R cross P, isn't it? Moment of linear momentum, like that we learned. Okay, so now we are going to consider we are going to find out the angular momentum about a fixed axis, or another relation for angular momentum with respect to the angular velocity, or relation connecting angular momentum and angular velocity omega. We are going to find out about in the case of rotational motion about a fixed axis. So here I am considering a rigid body and it is rotating about a fixed axis. O is the center. So here I am considering one particle P, and which is at a distance R from the origin. This is the perpendicular distance, so I am representing it as R perpendicular. So OC is the axis, through the axis the point is represented as OC, and this is CP is the point. So here we can, from vector, using vector addition, we can write it as OP equals, what is OP? OC plus CP. This is the vector, isn't it? So now we are going to, our aim is to find out the angular momentum. So how we can find out the angular momentum? L equals R cross P. So this diagram you will be familiar, right? In last video also we did in the case of work done. To find out the work done, we were using this diagram in the final stage, isn't it? So now also we are starting with this equation only. L is equal to R cross P. So what is R here? So for a particular particle, what is R? But R equals OC plus CP. Isn't it? OP is R, therefore R equals OC plus CP. Okay, so we are writing it over here. L is equal to, instead of R I can represent it as OC plus CP cross MV. MP equals MV, isn't it? M is common, so I can write it as M into OC cross V. So M I am taking it outside since it is a constant, and OC cross V and CP cross V. CP cross V. Okay, see here what is OC here? This is OC cross V. Velocity, in which direction it will be acting? It will be acting parallel to this, isn't it? So OC will be OC cross V. Okay, so V is, what is V? Is the linear velocity, isn't it? So in which direction it will be acting? It is acting along the tangent. So what is the direction? Angle between OC and BV, the angle between them, theta, will be equal to 0. Since they are parallel to each other, angle between them will be equal to 0. Since it is 0, this term will become equal to sine 0. A cross B, AB sine theta. Sine 0, 0, so it will become equal to 0. And then CP cross V alone will be existing. M into, what is CP here? CP is the R perpendicular component, isn't it? Cross V. Okay, so, but V we can write it as, what is V? V equals R omega, isn't it? So we can write it as R perpendicular component along, we should alone will be considered in this case. So L is equal to m into r cross r omega. So what is r cross r omega? R perpendicular, this is perpendicular to omega, right? So it is 90 degrees. Sin 90 is 1. So we can write it as m r square omega. So what is this m r square? M r square is the moment of inertia. We already learned it as I. So L is equal to I omega. This is the equation which we are getting. L is equal to I omega. Understood how we are getting this relation connecting L and omega? So we are considering only one particle in a rigid body, which is at the point P. Okay, that point P is from the origin, it is at a distance r. So we considered r, how much is r? L is equal to r cross P, and here only parallel component won't be existing, only perpendicular component will be existing over there. Okay, so m into r perpendicular V will be existing. But V is equal to r omega, we already know that. So substituting, we got it as L is equal to I omega. And we know another equation, tau equals dl by dt. This equation also we know, isn't it? So here instead of L I am writing it as d by dt of I omega. I is a constant, isn't it? So I can write it as I into d omega by dt is alpha. So tau equals I alpha. Like that also we can write down. This is already we derived tau equals I alpha. So this is another method to derive tau equals I alpha. So L is equal to I omega, we got it. Torque tau equals dl by dt. Instead of El we can substitute I omega. I we can take it outside. D omega by dt is alpha, angular acceleration. So tau we are getting it as I alpha. So clear? So these derivations are very important. L is equal to I omega and tau equals dl by dt. The tau equals dl by dt already we derived in the first video itself, isn't it? First video of system of particle itself we derived that tau equals dl by dt, and it's clear. So shall we move to the next one? So next we are going to derive this conservation of angular momentum. Conservation of linear momentum we already learned, isn't it? The same way we can state conservation of angular momentum. So how we can state this conservation of angular momentum? Conservation of angular momentum is, say we know torque tau equals dl by dt. Okay, if we are not applying any torque on the system, that is, if tau equals 0, what will be? dl by dt is equal to 0. That means L is a constant. If there is no torque acting on the system, angular momentum L remains constant. That is conservation of angular momentum. In linear momentum, conservation of linear, if there is no force acting on the system, momentum remains constant, we learned, isn't it? So same way here, just we are writing it as if there is no torque acting on the system, angular momentum will remain a constant. Okay, so tau equals dl by dt, and if tau is equal to 0, L is equal to a constant. Angular momentum, if we are not applying any external force, angular momentum will be equal to a constant, that is I omega will be a constant. I omega constant in the sense, if I is increasing, what will happen to omega? Omega will decrease. If I increases, omega will decrease. That is, if I decreases, omega will increase. That means, say, while we are say in somersault and all, or in this belly dancers and all, or in gymnasium, what they will be doing, they will be keeping their hands away from them, and at that time while they are taking a round, their velocity will be decreasing. At the same time, when they are keeping their hand closer to their body, at that time thus their angular velocity will be increasing. What will be the reason? While they are keeping their hands closer, what is happening? From the axis of rotation, if the hands are closer, distance is decreasing. If distance decreases, I will decrease, because I is equal to mr square. isn't it? So as r decreases, I will decrease. If I is decreasing, what will happen to omega? Omega will increase. When they are keeping their hands away, what will happen? R is increasing. If r increases, what will happen to moment of inertia? Moment of inertia also will increase, since I is equal to mr square. Okay, so as r increases, m also as r increases, I will be increasing. If I increases as per conservation of angular momentum, omega will decrease. So if they are keeping their hands away from them, then they will the angle of this rotational velocity, or that is angular velocity, will be decreasing. If they are keeping their hands together or too close to their body, then the moment of inertia will be decreasing and angular velocity will be increasing. Okay, so clear? So these are some of the examples for conservation of angular momentum. In park also you can see roundabouts. In roundabouts and all, while the children are keeping them close to them, then as if all are crowded and they are close to each other, then we can see the velocity will be increasing. But while they are moving away, what will happen? Angular velocity will be decreasing. While they are holding the hands here, and while they are moving away from that this playing thing, the roundabout, you can see the velocity will be decreasing at that time. Okay, so as r increases, that is from the axis of rotation, distance is increasing. At that time, moment of inertia increasing. If moment of inertia increases, angular velocity should decrease. Okay, so clear this conservation of angular momentum. Next is rolling motion. So when an object is rolling, what kind of motions are there in the case of rolling? So if an object is rolling from here to here, what will happen? So it's rotation also there, it is translational also there. Rotational and translational we should consider. Rotational plus translational we should consider in the case of rolling motion. Rotational means, see, if we need to find out the kinetic energy of a rolling object, what we should do? We should consider the rotational motion as well as the translational motion. Rotational motion, what is the kinetic energy? Half I omega square is the kinetic energy. In translational motion, what is the kinetic energy? Half m v square is the kinetic energy. So if we are adding these two, we will be getting the total energy in the case of a rolling motion. Okay, clear? So in this chapter, many derivations are there, okay, including the vector. Okay, so understand them properly and will do. Okay, and then now we are going to start with the numericals. I'll do 3-4 numericals from this chapter, which is relating to the parallel axis theorem, perpendicular axis theorem, and this moment of inertia also. Okay, clear? Here we are starting with the numerical, and first we will consider the 10th question. So before that we already did the particle velocity, that is center of mass and all we did. Okay, some important questions we will do, and then we will pass to the next theory portions of the next chapter. Otherwise it will be difficult to finish in this portion, isn't it? So after that, while we are doing revision, if you have any doubt, you can send it as a comment, then I'll do it. Okay. So now I am considering the 10th question. Okay, in page number 178. Find the moment of inertia of a sphere about a tangent to the sphere. Given the moment of inertia of a sphere about any of its diameter to be 2/5 mr square, where m is the mass of the sphere and r is the radius of the sphere. Moment of inertia of a sphere about the tangent we should find out. See, if this is the tangent, this tangent we should find out the moment of inertia about the tangent. We should find out. Okay, and for that, given the moment of inertia of a sphere about any of its diameter to be 2/5 mr square. So if this is the center of the sphere and it is given through the diameter, the moment of inertia is given as 2/5 mr square. So this is the moment of inertia through the diameter. We want to find out the moment of inertia through the tangent. Tangent means it will be touching only one point. Don't think it is here it is many points it is touching, because okay, it's only one point only will be touched over there. Okay, so that is moment of inertia along the tangent. So we need to find out the moment of inertia along the tangent. How we can find out this one? See, while seeing this itself, this diagram itself, you can understand these two are parallel, isn't it? So if it is parallel, so we can apply the parallel axis theorem. So what is this parallel axis theorem? Parallel axis theorem states that moment of inertia of an axis about a particular axis will be equal to the sum of moment of inertia of a parallel axis passing through the center of mass and mass of the object and the square of the distance between the two axes. So what is this distance between these two axes? It is radius. So we can write it as r square. Okay, so here this is center of mass, isn't it, through the diameter which it is passing. So ICM, that is diameter through diameter, it is 2 by 5 mr square, and this is mr square. Okay, so while we are solving this one, we will get it as 7 by 5 mr square. Okay. Clear how we are finding out this parallel using parallel axis theorem? If you are reading once and drawing the diagram, you can easily identify. Okay. Next, B part is given the moment of inertia of a disk of mass m and radius r about any of its diameter to be mr square by 4. Find the moment of inertia about an axis normal to the disk and passing through the point on its edge. See. First one is, the B part is, moment of inertia of a disk about its diameter is given. Moment of inertia about diameter of a disk about diameter is given as mr square by 4. We need to find out the moment of inertia normal to the disk. We should find out. So if this is a disk, we should find out the moment of inertia in this axis. How we can find out? That is perpendicular axis theorem. So to find out this one, we can use perpendicular axis theorem. Perpendicular axis theorem states that what is the, yes, moment of inertia about normal is equal in a plane lamina. If we need to consider the moment of inertia perpendicular to it, what we can do? We can add the moment of inertia of the axis which is on the plane lamina, ix plus iy. So while we are considering a circular disk in this manner, so if I am considering the two perpendicular axes, what will be these two axes? That will be through the diameter, isn't it? So if I am considering a plane like this is the planar lamina. Okay, in this planar lamina, if I am considering the two axes, this also a diameter and this also a diameter. Okay, so what will be the sum? Yes, sum of the diameters, moment of inertia of the diameter. So mr square by 4 plus mr square by 4. So 2 mr square by 4. So we will get it as mr square divided by 2. This will be the moment of inertia along the normal. Now the next one is, and about an axis, moment of inertia about an axis passing through a point on its edge. We need to find out the moment of inertia through this. How we can find out? We can find out using parallel axis theorem. How we did this, isn't it? So the second part, how we can find out the moment of inertia? Moment of inertia will be equal to moment of inertia along the parallel axis passing through the center of mass, that is moment of inertia along either x-axis or y-axis, any one axis we can consider. Here I am considering y-axis. Why? Because it is parallel, right? So Iy plus, then what will be total mass of the disk and the distance between the two axes. Distance between the axes is r square. So it is Iy, what is Iy? mr square by 4 plus mr square. So we will get it as 5 by 4 mr square. Okay, clear how we are. So while identifying the question itself, so while reading the question itself, you can identify how we will be doing it. Okay, clear? So I hope all of you understood all those things. I'm winding up for today. If you like the channel, please don't forget to subscribe. Thank you for watching. Bye.